Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the AAS Journal Author Series. And I am super happy to have Nuria Jordana-Mitjans with us today. Hey, Nuria.
Hello. Hey, everybody.
Where are you located at, Nuria?
Well, now I'm located in Barcelona, so there is no snow here, but close by in the Pyrenees, it's quite 10 degrees. So we have a little bit in the tips of the mountain. So it's
Very
going
nice.
to wait. Yeah.
I thought you were going to say New York City, given that picture behind you there. So
no, I wish.
Have you been to New York City or?
Yeah. When I was a little kid, I went to New York City, and just after that trip, I went past a shop and I saw that picture. I was like, oh, that's so nice, and I just bought it. So
very cool, very cool. It is January 30th of 2023 as we record this. It's definitely winter in Phoenix, and like Spain, Barcelona, we have no snow on the ground, but it is a little chilly out in the morning today, so it's all good. Super duper. And
so nice.
Maria, what do you like to do for research?
Well, basically, during my PhD and now in the postdoc, I'm doing gamma ray bursts. So I find that very, very interesting and keep following on this research. And what I study about them is how these, basically these jets are launched from the central object. So in gamma ray bursts, what we have is basically the merger of two neutron stars that actually produce a GRB, or we have collapsing massive stars also producing GRBs. When we end up is with a disk, a central object, and two jets. So I study how these jets are produced with polarization studies at early time. So I use robotic telescopes to actually catch the light in the first instance after the explosion, so cool. Seconds to minutes after the burst. And that tell us, the polarization properties tell us if we have magnetic fields or not. Or we have these magnetic fields ejected from the central object, or basically the magnetic fields are locally produced in shocks. So basically the final question is if large-scale magnetic fields ejected from the central black hole or magnetar can drive this explosion. And apart from that, also these early time studies can provide also some information, as you will see in this paper, about the nature of these central objects. So if we have black hole or magnetar remnants, more or less.
Very cool. Very cool. That's a big topic. Very awesome. And that is going to bring us to this very awesome APJ article. It's open access, people. Go get it for free these days. A short gamma ray burst from a protomagnetar remnant. And Nuria, take us away.
Yeah, so basically this was the last work of my PhD, and it was done with the Liverpool telescope people. So you can see them Carol Mundell, Cristiano Guidorsi, and also we have Ian Steele and Andrea Gombok and Sio Kobayashi here. And this basically is the people we do these early time studies of polarization studies of GRBs. And we also have here Enrico Ramirez-Ruiz and Brian Metzger that also contributed to this case because it was interesting from the point of view of this central remnant. And also it was very interesting because we got data from the Large Binocular Telescope, and that was thanks to Andrea Rossi that you can see here, and also Barry Rothberg, that actually were the link with the telescope and the ones that actually did the analysis. So it was really nice because we actually managed to get the redshift of this event thanks to them. So cool. Congratulations for that. Yeah.
Very nice. Good shout out. Good shout out. Okay.
So yeah, in this case, what we had here, so basically the title tells you a little bit the story and it spoils you a little bit the end. But what is interesting here is that we got a short GRB with extended emission. And this short GRB with extended emission, short GRB means we have the merger of these two compact objects. And extended emission is something that follows the short GRB. And it is interesting because it's extended gamma ray emission following a short GRB, which is not supposed to be there in the traditional model. So it's long after the dynamical timescale of the merger. So there should be something else powering that extended gamma ray emission.
Fair enough.
And there's a lot of models about that. So we have accretion, prolonged accretion from material that was ejected per merger, things like that. And we also have the possibility that we have a long-lived central engine, and having a long-lived central engine also usually means having this magnetar transient magnetar sometimes that they call it, that actually powers additional energy to the system. And so it is interesting because actually these short GRBs with extended emission are only like about 1% of the total detected by the Swift Burst AAS telescope. So we have very low chances of detecting these events. And we managed to get that data with the Liverpool telescope. So that was really, really nice. And as you will see following, what we actually detected was a little bit puzzling because we didn't expect that properties of the emission.
Okay.
Well, apart from this, the GRB is also very interesting because the high energy properties were quite special. They were like, it was a very bright event and it was very hard. Well, meaning hard, as you can see here in figure 1.
Figure 1, let's take a look at figure 1.
Here, yeah. So basically you can see here what I described. We have a very short, hard gamma ray prompt. You have like a very short spike that is 0.3 seconds, which is something that is expected from short GRBs. Okay. And we also have this extended emission, which is soft. So we have that the energy is shifted to lower bands. We have a hard gamma ray prompt with energy shifted to higher bands. And then we have the soft extended emission with energy shifted to lower bands. Okay. And this actually tells you more or less that you have these two components. And as you can see here, the energy peak, well, the peak energy here and in the left, actually rise from 500 to nearly 3,000 keV here. And that actually is quite hard for even a short GRB. So it's quite special because it was one of the hardest of the short GRB population too. Okay. So at the end, the high energy properties, it told us that what we had here is this short event. So we have the merger of two compact objects, and the extended emission is actually gave us like a science case to work on and try to pin down which was the origin of this. So yeah, so maybe moving to this figure 2.
Figure 2, observations,
yeah,
reaction, and figure 2 like curves. Okay.
Yeah, so what we saw in the beginning was something like this, which is maybe if you're not in GRBs, it doesn't seem so, like it does not pop up as something very strange. But what we have here, well, first I will present the data. We have here in black the Burst AAS telescope data, so the gamma ray data. We have here in purple the X-ray data. And we have here in colorful, colorful colors like blue and blue and purple. And so we have the U-boat data, so also data from the Swift telescope, but the ultraviolet telescope. Okay. And also in green and yellow, we have the Liverpool telescope data. Okay. And what is interesting here is that basically so we show here the gamma ray extended emission that actually lasted up to 50 seconds. And the X-ray data actually was a bit flat in the beginning, as you can see here, and it quite steepened at the end of it a little bit. And the steep was like 1.9, which like the temporal decay of the emission is 1.9 approximately, which is something that is quite steep for what we expect from the synchrotron spectrum of the afterglow. Okay. So it's similar to what we have when we have a jet break. So basically when we see the edge of this jet. So that's quite puzzling at early times to see that. For us it was. And what we have here is that the emission is very flat in the beginning and actually steepens at the end. And what we see in naked eye, that maybe it's not so obvious, so you will see later in other feeds, is that this emission actually broke in by several bands. So first we have a break at ultraviolet bands, and then we have a break through redder optical bands, basically. Okay. So we have here something weird. So we have very flat emission, and then an actual break at 30 minutes after the burst. Yeah. And this is, if we think in terms of what we expect, so what we expect in reality is that, well, maybe I can show it like this by hand. So you have the central object and you have the jet, and then you have prompt emission. This is the gamma ray flash. And this is due to internal shocks in shells. And then after all, this jet gets decelerated by the surrounding circumburst medium. Okay. And when this jet gets decelerated, it produces something like an afterglow, well, it's what we call an afterglow emission. And this is produced by a pair of shocks. So we have a forward shock that travels into the interstellar medium,
Yes.
and a reverse shock that travels backwards into the jet. So
Yes.
at the end, what we should see in X-rays and optical bands is a composition of the reverse and forward shock. So
Okay.
the reverse and forward shock have some special scalings. So the emission and the spectral properties need to fit some like characteristic scalings. And usually the decay is about 2 for the reverse shock and 1 for the forward shock.
Okay.
And as you can see here, the X-ray is already 2. And that could say, oh, maybe it's reverse shock, but it was not. And then the optical is very flat. So we have 0, and then it decays to up to 4.6. So the break is very, very, very steep. And it does not fit with the idea of this being synchrotron emission.
Okay.
And also, if we look here, you're looking at the photon index, I think. So
Yes.
if you look at the photon index, the optical emission, which is the green one, suffers a very steep, it does increase a lot. So we have that the photon index first is nearly 1, and then it progresses to 4. So we have this kind of dip. So this is not expected from the synchrotron spectrum of the afterglow either. So this is something very weird overall. So this is what we try to investigate and interpret in this paper.
Okay.
So, so yeah, maybe figure 3 now.
Figure 3. Got a nice table of the optical photometry and figure 3. Here we go. Where are we here? Let's take a look.
Yeah, so yeah, this figure is very interesting because before trying to understand all this, we need to actually get to know which are the energetics of the GRB. So the energetics are highly depending on the redshift, so the distance of the event. And here, from the optical data, we basically got like an upper limit on the redshift. We got an 1.5 2 sigma upper limit on the redshift, because meaning that if you detect the emission in the optical and ultraviolet, actually you have the redshift, the Lyman break at some point. So you can you actually put a constraint on the redshift. Right. And what was interesting is actually to try to figure out where was the host galaxy. So if we manage to find the host galaxy, we will be able to put the proper distance to the GRB. So what we did here is use the Large Binocular Telescope, and you can see here we did some photometry, some deep photometry. So the idea here is that we knew that there was the G3 galaxy. It was from the LTSS catalog, and it was a galaxy at 0.5, more or less. So what we were interested is to see if there was another galaxy that actually was more likely to be from that one. So what we detected with the photometry is these 3 galaxies. And what was very interesting is that using also spectrometry, so we put a slide on top of the G1, G2. So we got a spectrum in the same time, so a 2D spectrum at the end.
Got it.
And we got like the redshift more or less of the 2 of them. So the G1, we actually managed to find some oxygen line, emission lines from the galaxy. And the G2, we didn't find this oxygen line, so it was redder, as you can see here in the C plot. So, well, the B plot is the R band, I think is the R band, and the C plot is the SZ band, I think. So you can see that G2 is more red. So in G2, what we did is that we actually found the Lyman break limit. So that told us that we have approx also 0.55 of redshift. And maybe I think if we go to the next one, I think it's already the spectra. So you can see actually the emission lines from the galaxy.
Figure 4.
Not yet. So figure 4 is the photometry. It's figure 5 already.
Figure 5. Yeah. All good. I'm with you. Yeah. Okay. Ooh, classic. All right.
Yeah. So here, we have the also the emission skylines. So the first panel is the spectrum, or the 2D spectrum. I think. Yeah, 2D spectrum of the 2 galaxies. So you can see here the first line. You can see the 5,800 angstrom
O2.
is one oxygen line.
Forbidden.
And then we have the 7,800 one. We have the second oxygen line. And that told us that that galaxy, so the G2 galaxy, is actually at redshift 0.554 or something like that. So that it wasn't very interesting, because actually it means that the three galaxies are the same redshift. So it was hard to mess up in like saying that one was from the other one.
Right.
The three of them were actually at the same redshift. So that was really interesting in this case. And what was really nice is that also we found out that the GRB was at the outskirts of a galaxy. And this is very interesting in terms of short GRB evolution. So what happened with short GRBs is that the progenitor is this 2 neutron star or neutron star black hole that actually merge. But before that, these things are born in supernova explosions. So the supernova actually gives natal kicks to these binaries. And actually what this happens is that they kind of get kicked out of the host galaxy. So the birthplace basically. And they end up being found out outside of the host galaxy and things like that. So this is the kind of environment we expect from them. So that was also interesting, because it actually proved again that we have this short GRB from a merger. So that was nice. Yeah. So I think maybe now the next plot, maybe. So it should.
Nice. So figure 6 is some Ringo 3 BBs. Yep. Yeah.
So now that we have more or less like the distance and everything, and we went back to the mission.
Yes.
So here you can see again that we have all the emission, all the optical ultraviolet emission here. And here you can see more with actual fits that the break is chromatic. So basically we fit everything with the same break time and the same slope as we will expect from synchrotron emission and everything. And we found out that basically this upper limit was actually very low. So it was, I think, some sigmas away. I think 3 sigmas or something like that away from the actual fit or something. Yeah, something like that. And also, what was very interesting is that the Ivan, so was actually underestimated. So here actually it gave information about that how chromatic was this break, and actually it was a significant fit. So maybe moving to the next figure, I think on the right, I saw it. Yeah.
Oh, there we go.
Here is when we derived the photon index, and we saw this chromatic effect. And actually this is what we saw in the other figure as a photon index. So basically this here we are providing all the information about these fits.
Nice. Very good. Cool. I'm with you.
Yeah, and then maybe figure 8 now.
Figure 8, we're in the reds. Ooh, we got some contouring for Z, function of extinction.
Yeah. So now we are just going through all what maybe I have said already, but here is when we also use this optical data and ultraviolet data to actually put an upper limit on the redshift. And this is, so the idea is that it is hard to put to estimate the redshift from the optical data and X-ray data and optical and ultraviolet data alone. You need usually the X-ray data to actually, fit the slope and everything. There is usually a degeneracy between the slope of the spectrum with the extinction. So using X-ray data actually fits the slope, and then you can get the extinction, and then you can estimate a little bit more the redshift. The problem here is that because we have like some very strange optical emission and quite strange X-ray data, it's not that I will not fit both of them at the same time, because we don't know if we have an extra component and everything. So in this case, we went to like a sensible scenario, and we only fitted the optical data. And what is interesting is that even so, like even only fitting the ultraviolet and optical data, you can still derive pretty good constraints. So what we did here is actually make sure that this GRB was not from high redshift origin. So the upper limit was of 1.5 in this scenario, as you can see here.
Okay.
So here you can see the contours of redshift and extinction. And here you have for the different photon indexes. So these contours actually put this 2 sigma upper limit on the redshift that you can see in the y-axis. And it's telling us this, that we are likely sure that that was the host galaxy because the afterglow emission actually fulfills this requirement.
Okay.
So
good.
So yeah, and I think on the right is the same. So it's just to show people that what happens if we put different redshifts. So you can see that redshift 2 already just gets the cutoff.
Bang, boom.
Yeah.
Yeah.
Like you will not be able to detect anything at these ultraviolet bands if we were at redshift 2.
Right.
So yeah, that's
cool.
Thank you. So yeah, I think maybe the next one.
And we got some photon indices in table 2 and figure 9, high energy properties. Okay.
Yeah, and well, basically here what we did is to actually compare the high energy properties of this event with other GRBs from the Fermi catalog. So first one I think it's just from the Swift Burst AAS telescope, I think, yeah. And the second one, and the second one and the third one is with the Fermi telescope. So this choice of plotting different data is because the Swift Burst AAS telescope, the energy range is at lower bands. So you have, I think, within 15 to 350 keV, and then Fermi reaches the MEP domain. So that's interesting because you can properly estimate the slope of the spectrum, and you can also determine the peak energy of the GRB. So that's why we choose two things, basically. This is how maybe panel A is how you traditionally display it, and then B and C just to show the property of the spectrum. And what you can see here is that, well, this GRB was very energetic in terms of fluence. Well, yeah, in terms of fluence, not so much, but in terms of flux, it was really energetic. And the peak energy on the panel C basically tell us that, well, it was one of the most hard events, so very high frequency peak energy. And the photon index was quite, was average in terms of short GRBs. So I think this actually told us that, so maybe I didn't tell that, but the blue things, so the blue dots are the short GRBs, and the gray dots are the long GRBs. So you can see overall here that basically the GRB fits with the short GRB distribution again. So yeah. So yeah, maybe the figure 10, I think it will maybe tell us more about, I think, the high energy properties.
Rest frame energy.
Yeah, because now what we have is actually we have the descent of the GRB, so you can actually get the intrinsic energies and things like that. So what we have here is the rest frame peak energy, and we have the rest frame. It is rest frame. So we have the isotropic energy here. So what we see here is, again, in gray we have the long GRB distribution. And we have in blue the short GRB distribution. And we try to fit here is the short spike and the extended gamma ray emission. So you can see that the short spike is one of the hardest energetic, well, maybe not so energetic, because you can see here that you have all the other short GRBs, but it is hard in terms of short GRBs. And we have the extended emission. It's similar to long GRBs. But overall, what we see is that this short spike is actually, I think it was 6 sigmas away from the long GRB distribution, making this case actually a short GRB again. So we are going over the same thing, but I think at the end this was
all good. It's all good.
Yeah.
More evidence, the better, right?
More evidence.
You got to keep, batting the case down. So it's good. Great. Very nice.
So.
And 11, these are your
so this is the nice bit that all the interpretation comes out again. So what we try to do is try to figure out what we were seeing, because if it's not fully synchrotron emission, the break and everything, the optical break was quite popped out our eyes. So what we are actually detecting. So this fit was inspired by cocoon emission. So this is actually a thermal fit. So we fit a black body emission here for all the time slices we could that we have contemporaries OBOT data, and at the end we only had optical data, but in the beginning it was like an OBOT data to optical data. And you can see that actually the fit was quite good in all overall. So the thing is like how we interpret now that, because if this is thermal emission, do we have actually a theory that actually can tell us that what we are seeing? So yeah, maybe I think figure 12 will be nice. So so basically it was what we tried to figure out is what was that. So if it was not fully synchrotron emission, and we tried some cocoon models, and we found that because we got the redshift, that basically a cocoon will be 3 magnitudes in the optical less. So this could not be the jet cocoon. So the jet was not actually responsible for this emission. So there was other theories like it was quite interesting, is that if we actually have a magnetar, so a remnant magnetar from the neutron star merger, what could different kind of emissions, we could see different kind of emissions from this case. And the case was basically if this magnetar is able to power the short GRB, and this magnetar is also, there's some theories that actually is able to power the extended gamma ray emission. And because basically what we have from the merger is that, well, you have different material ejected at different directions. We have the material tidally ejected. We have the material radially ejected at the contact regions of the 2 neutron stars when they merge and they hydrodynamically eject up. Then we have the ejecta from the disk, so the disk wins. And overall, all this, and after the short GRB, we have basically different. So we have different distributions at different points. So we have some less mass, expected less mass at polar regions, more mass at equatorial regions, and this can actually collimate the winds of the magnetar. So actually, this can actually power more, not as collimated jets as the short GRB, more open. But actually, this is able to power the extended gamma ray emission. And after that, when the spin down luminosity of this magnetar, so this magnetar is spinning and slowing down, basically, when this happens, these jets get stifled behind this ejecta. And what happens is that behind the ejecta, so we have these shells, and then we have the jets. Actually, it is created a per positron nebula. So per person electron nebula. So what happens is that this nebula actually radiates via X-rays. These X-rays, via synchrotron and inverse Condon, and this actually produces X-ray emission that actually gets absorbed by the ejecta wall, the neutral ejecta walls. And these actually then, these reprocessed photons actually are able to emit at optical and infrared wavelengths. So what we end up trying, what we try to figure out if this was the actual scenario of this. Right. So looking, I think it's figure 12, I think it is.
Let's look at figure 12, effective temperatures. These are effective temperatures.
Yeah, it is this one. Yeah, so we try to figure out if this was actually the scenario, because at that point it's like, well, we keep trying models, but none of them actually work. So what we have here is that actually from more or less 600 seconds post-burst, the emission starts to follow up these scalings expected from having a magnetar nebula. So we have that the luminosity actually is following the spin down luminosity of the magnetar. The radius is linearly expanding. And actually, if you put all this into the equation of the black body, then you get that the temperature is actually following this -1 decay that is expected.
Cool.
So the thing is the problem is like what happens with the first like seconds of the emission. Like we need to try to figure out what, it's not following what we expect, but at later time. So the last I think it is 15 to 60 minutes is actually following what we expect.
Okay.
So I think maybe it could be figure 13 or something like that, maybe.
13 are the X-ray light curves, it looks like. Flux densities.
I think maybe later.
14 spectral energy distributions. Sets.
Yeah, the spectral. That one is a nice one. So we tried here so we actually tried to do more fits, this time with the X-ray emission, because now we had fitted the optical, and we know that at some point it does fit the expected scalings of this nebula, but we try to figure out if actually if we put the X-rays, if that would actually help or not help the interpretation, and what happens with the first 15 minutes of the emission. So what we did here is just to figure out what will be the best fit. So if we have a break or we don't have a synchrotron break. So if we have the cooling frequency or we don't have it. So, and we find out that it is quite important to have this break. So you can see that the residuals of the first plot, they are not quite nice. So it's not a very significant plot, significant fit. And for the second one, when you add 1 degree of freedom, it fits better, basically. So this is just phenomenological. So we don't have any physical model here.
Right.
And if we move to the 15th figure, I think is this when we end up start to put like physical models into it.
Okay.
So we tried different physical models, and we end up finding that the forward shock, so reverse shock is quite discarded at this point. So we found out that the forward shock synchrotron scalings were quite good, and we tried to figure out if it was like slow cooling and fast cooling regime. We found out that slow cooling regime was better from the fits. And it was also, the fits also favored an interstellar medium. So also this makes sense with the environment of the GRB. Okay. So usually you can have a wind medium, but it's more related to like these massive stars. Interstellar medium is what we expected. So that actually also fit the interpretation.
Yeah, that would be
and also we found out that in the best case, we needed like the cooling frequency in between the X-ray and the optical. And this, I think this is the B plot, but then it was, if you see that, it's not good. If you look at the residuals, this more physical fit actually gives you very bad results. So it is one of the best one of all these trials, but it's not good. So we ended up like actually having to put this thermal component. So if we add the thermal component, we get back all the scalings as we have derived before. And also it gives you a good fit. So actually this fit is significantly good, better than the other ones. So what actually tells us this fit is that we have synchrotron emission from the forward shock, the first 15 minutes, and from the last 15 minutes to 60 minutes, we have this thermal component. So actually it was nice because actually it makes sense. Everything was like, I was quite happy saying, okay, yeah, like the story kind of holds still.
Yeah, right.
And what we try to figure out also is, if you, I think now you will need to go up. I think it was 13 figure, I think.
Let's go 13, yes.
Yeah, this one. So this is the last kind of fit with it, is to figure out more. So you can see with the spectral energy distributions, we have fitted up to more or less 1,000 seconds. But as you can see here at the end, we have a kind of a significant rewriting in the X-ray. So it's I think it's 4.6 sigma. And we try to account for that as well, to try to figure out what was that, because there are some short GRBs with extended emission that also have this rewriting. So it is interesting to try to figure out if this could also be accounted with the scenario of the magnetar. Yeah. So what we did is actually, we just fitted a pulse function, and we just try to figure out when this thing happens. So, and we tried also to explain that. So the thing with this is that basically in this scenario of the magnetar, at some point, if we have low ejector masses, as in this case, so we have so we estimate the ejector mass at some point, I think here in the optical emission like fitting. So from the constraint of the optical depth and so on, and you can derive the ejecta mass of this shell that actually radiates thermal emission at some point. And we find that this this ejecta mass is 10 to the -4, something like that. So this is quite low. And if this ejecta is quite low, and also we have quite powerful magnetar winds, as in this case, at some point, the magnetar winds are able to ionize this ejecta, and then you can directly see the spin down luminosity of the pulsar. So this actually makes sense. So what we see here, this rebrightening, is actually we are seeing the spin down luminosity of the pulsar. And we did a quick estimation just to see if all these components can all tell us how it is the magnetar and everything. So basically, using this X-ray late time rebrightening and also the optical plateau that we see at the very beginning that is quite flat, and using also the extended gamma ray emission, we derived, I think that this pulsar was about 4 milliseconds period, had to be 4 milliseconds period pulsar, and also with a quite high magnetic field. I think it was 10 to the 5 and per 10 to the 15 or something like that Gauss. So actually this thing actually gave us a lot of information about the characteristics of the pulsar.
Cool.
And I think the interpretation is done more or less. So I think the end of it is the discussion, which has also some juice about that, because actually it's quite interesting that we could find traces of this magnetar in this system.
Yes.
And there is so basically there is some good things and bad things. So observationally, there's been many traces there's been some traces of having magnetars in short GRBs, but there is some theoretical problems. Here is that in simulations, so mergers actually, so magnetars from mergers are not able to actually produce short GRBs, and that is because magnetars have these strong winds that actually can choke the jet. So there is still some work that needs to be done in this sense, like how we can like get maybe like some results that actually prove that these things can actually power short GRBs.
Yes.
And cool. And I think it is nice, but also it requires this extra work of how observations and theory can actually merge together and how we can interpret this a little bit better. And I think you went to the 16 figure that I think it's it shows everything I have said so far, so I can go maybe and summarize it there.
Sure.
Yeah.
So where do you want me to?
Yeah, here. Yes, perfect.
Okay.
Yeah, I think so. Here, is more or less what I have said. So in a panel, you have this merger of the two neutron stars, basically merging together and actually releasing the different material at different directions. You have here in red the tidally ejected material. You have the radially ejected one, and actually at some point these two neutron stars produce the remnant. The remnant is expected, so from these neutron stars you have different remnants expected. You have from high mass binaries, you have that actually this produces the prompt collapse to a black hole, but not in a lot of cases. I think it's less than 3% of the cases you will have the prompt collapse to a black hole. Then in most of the cases, I think up to 70%, it is a very like constraint, like 0 to 70% of the cases, you have this hypermassive neutron star. So hypermassive neutron stars actually can only live like 100 milliseconds after the burst, and they collapse. So this is not the case. In this case, what we have is a supramassive neutron star. So supramassive neutron stars are able to survive the merger for longer, and they can live up to a day or something like that. So in this case, what we have is this supramassive neutron star, And this is able to power the short GRB through accretion or enhancing the spin down luminosity, again, through accretion. So at some point, this actually the ejector is able also to collimate the winds of this magnetar.
Yes.
And actually is able to power this extended emission. So at some point, what we have is also that the winds, actually the energy of the winds decrease. So the luminosity of these winds decrease, and actually these jets get choked by the ejector. And this is what we have when we have these nebula, this electron positron pair nebula. And this is when this X-ray emission gets reprocessed, and then you produce, well, this thing produces the optical infrared emission. Cool. And at some point at the end, and when this winds, so in our case, it's up to, it could be hours to 1 day post-burst, and you have this ionization of the ejector. Yes. And actually, this is how we see this X-ray bump at the end of it. So this is the final picture of it. And
cool. Very cool.
Yeah, and at the end, maybe in this case, well, I think it's really nice if we could do like in the future to do some extra observation of these events, so especially targeting these events, because I think we could see weird traces of these extra emission components from this magnetar. So the final discussion here will be like how many and how much of these magnetars can survive these mergers of neutron stars.
Right.
So yeah.
Very cool. Very cool. Very cool. Nuria, thank you so much for walking us through your very lovely article. I appreciate it.
Thank you.
And you mentioned it a little bit there, but let me just push on at that a little bit. And let me ask it this way. So where do we go from here? Let's say over the next couple of years, are there additional, perhaps protomagnetar GRBs in the pipeline? Do we go hunting for them? Are there additional theoretical models to be done? Sort of what are the next steps over the next couple of years on this fascinating topic?
Yeah, like it will be interesting to actually follow more of these events. The only problem is like it is 1% of the burst alert telescope cases, so it's not likely. Maybe every year it could be one, but it's not, because Swift detects about 100 every year. So at the end you will have one of these events per year, but it's also you will need to improve the optical follow-up of these events with robotic telescopes, because actually we have the Liverpool telescope that follows in the northern hemisphere, but also it will be nice to have more of these robotic telescopes that actually are able to follow these things. So you have 1 chance 1 year, so it is quite hard to get them. And also it is quite, I have not said that, but actually these things are quite not bright. So you have long GRBs, they have brighter afterglows, and these cases are not that bright. So Liverpool telescope is already a 2-meter telescope, and we were able to detect them with it. The only problem is that like these short GRBs, it is already 18 magnitude at the optical wavelength. So most robotic telescopes are quite small. So it's like small to intermediate. So this is already the domain of these big telescopes pointing to these events. And actually in our cases, if we had a big telescope, like we will have missed up the first 30 minutes, which actually gave us all the information about it.
Yeah.
So
good.
So I think, like maybe we will need more like 2-meter telescopes robotically. Actually pointing towards it. So in this case, I think it is nice. The only thing we can improve is to have more like robotic observations of these things, and also maybe follow up triggers from Fermi, because Fermi detects more GRBs, and the only problem is the large uncertainty errors. So it's degree. Yeah, so you cannot follow up with very small fields. You need actually degree fields to actually be able to see them. So you have this, you can keep, we can keep doing these things. The only thing also is that this event actually gives information that in optical, like fast cadence optical surveys, we will also be able to detect them. So you have, in this event, we saw the jet and everything, but because we have a magnetar, having a magnetar in the middle also gives us information that we will have seen a kilonova 100 times brighter than a regular one. So this could have been seen with fast cadence surveys, kind of in the optical. So
Yes.
even without having the GRB, we should be able to see these things. So I think maybe in the near future there is winter, I think, in infrared that will actually be doing this kind of surveys. We have a lot of fast cadence surveys, maybe Assassin and things like that. The only things is like, how you figure out that thing was actually a very enhanced kilonova. It's hard to say that, but yeah. And in the very fast future, I think LSST and then also the Roman telescope will be nice.
Very nice. Cool. Well, I look forward to seeing this topic move forward. But congratulations on that very nice discovery of Protomagnetar gamma ray bursts. Very nice. Nuria, thank you so much again for walking us through your very lovely article. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Bye.